To the session on from functional to reactive programming. So, just to give you a context of what this presentation is about, it's more of a journey of me learning about reactive programming. So, when I first got into getting introduced to reactive programming, I was as confused as anybody else could be, trying to understand what reactive programming really is. And as I was struggling with it, what made it even more difficult for me is a lot of documents that talked about what it is, but quite did not at the time show me how to actually make use of it. I'm a programmer at heart. If I cannot see something in code, it just doesn't click into my mind. So I was struggling quite a bit trying to understand what reactive programming was. And what I'm going to share with you today here in this presentation is more of my journey in terms of learning about reactive programming. So I'm not going to get too technically deep into anything here, but more share about my realization of some of these ideas. Now, one of the things, there are a couple of things I've realized over the years in my life. And one of them is it's relatively easy to learn a syntax. It's relatively easy to learn a new API or a new library. But what is really hard oftentimes is understanding a new paradigm. Paradigm shifts are really hard for us because it requires us to rethink and change our thought, change our way that we approach solving problems. So paradigms are very critical and important. But in my life, I've probably seen about 6 different paradigm changes over time. And when I started programming, that was the very first paradigm change for me, even to realize that you could actually make machines do something by writing code and writing instruction. And of course, I was a very young a person at that point, trying to really write code to make things work. And my very first exposure to programming was in procedural languages. So that was my first paradigm, is writing code in procedural code. And then, of course, along the way, learned about procedural and structured programming. The second paradigm shift for me was to learn about object-oriented programming and trying to wrap my head around polymorphism and inheritance and encapsulation and how to really structure the code to use effectively object-oriented programming. My third programming paradigm is something I would not wish on an enemy today. I had to spend years programming in COM and Corba. This is one thing I'm fearful today if my children will ever find out that I once programmed with COM. And the point really is, it was not that it didn't work, it actually did. And that's what was frustration, because it worked, but I didn't understand how it worked or why it worked. And I remember waking up every single day with this fog in my mind, trying to understand how these objects communicate across the wire, across to each other. And if anybody wants to use the word object factory, I'll be really angry again because I've seen enough of them. But for me to actually understand how the remoting actually worked, and I had to do this by writing code in C all the way through. And when it worked, finally, I'm like, oh, I get this. And that was a huge paradigm shift for me, learning about distributed computing and COM and Corba. My next paradigm shift, honestly, was even more difficult. And that was trying to program in Node. Yeah, I've programmed in JavaScript for a while. I fairly understand JavaScript. But when I started programming in Node, that was really hard because most of my experience until that point was writing code in languages like C++, in Java, and C#. But to write code in Node using JavaScript was mind-bending for me because I had to understand asynchrony rather than parallelism. It's not that asynchrony was really hard, but my trouble again was learning how to write code that is asynchronous, not just calling asynchronous code. And that was really hard for me. And my next paradigm shift, probably the fifth one, was trying to learn functional programming. And what really made this worse is all the people doing functional programming kept telling me, oh, that is so easy. And yet I was finding it so difficult to do it. And every time I sat down to program in functional style, it was hurting my head because my mind was wired by then to think about imperative style of programming, whereas to try to think about in terms of straight transition rather than state mutation was incredibly hard. And I have to say that today I probably can solve problems in functional style about 50% of the time. The other 50% of the time, I still have to struggle to bend my mind to think in functional style. A case in point, on a flight not long ago, I sat in a flight. It was a cross-Atlantic flight, and I had about 9 hours on my hand. I took a problem when I sat down on the flight, and I wrote the code in about 15 minutes using imperative style. It took me about 8 hours more to write the code in functional style. I would be struggling with it, trying to understand how to write in functional style. And at the end of 8 hours, a sudden light bulb goes in my head. And within minutes, I had the code working in functional style. Trust me, trying to solve a problem like this is a lot more entertaining and exciting than watching in-flight entertainment. So the point really is, in this case, it can be really hard to understand and conceptualize problems around functional style. And my most recent paradigm shift was actually reactive programming, trying to understand what reactive programming really means. In that regard, when I started looking at reactive programming, I was asking the first question I asked was, why in the world do we need yet another programming model? And it took me a while to realize that in our field, we come up with new names for what we do every few years for what we already do and get really excited about it. And this time around, it is called reactive programming. And so as I was struggling with this, I came to a realization about what reactive programming was, and that's what I want to talk about now in terms of functional programming and reactive programming. So to lay the ground for it, here is my assessment of reactive programming. So to me, reactive programming is really what I want to call as functional programming, and I'm going to say plus plus. So in other words, to me, reactive programming is really an extension of functional programming. Now, clearly, people may argue and say, well, can I not write reactive code in a procedural language or even in an object-oriented language? And the answer to that question is like asking the question, can I not write object-oriented code using a procedural language like C? And the answer is yes, you can, but nobody survives that. So the point really is that when you think about reactive programming, and I'm going to make the case why I think reactive programming is really a functional programming plus plus, because all the signs of it kind of build up to it. And once I kind of clicked in my mind, it became a lot easier to understand this moving forward because I was able to really write on the knowledge of functional programming I had by that time and build on top of that. So let's talk about functional programming really quickly before we talk about reactive programming, as I'm going to draw this relationship. So what is functional programming? Now, when you talk about functional programming, you often hear people talk about a few things together. So what is one thing we all have heard beaten over our head over and over when it comes to functional programming? And that is, they tell us we should really honor immutability. And we are told that we should not mutate variables. We should not use shared state. So we get used to this idea of immutability quite a bit from early on. The second thing that we learn about in functional programming really is about the so-called higher order functions. So what are higher order functions? Higher order functions are really typically, this is where it leads to. I'm going to call it as a normal function or regular function or just a function. And what can you typically do? We may pass object to a function, and we do this quite often. And we may create object in a function, and then finally we may return object from a function. So this is what a normal function is that we normally use to write our code, and we are used to building applications with these things quite a bit. Well, that takes us to what we want to call as really higher order functions. So what is a higher order function? An higher order function is where we may pass a function to a function, we may create a function within a function, or we may return a function from a function. And that's what makes a function a higher order function. So higher order functions have the ability to receive objects or create objects internally or return objects as well. So much like how we we can pass objects around, we can pass functions around as well. So as a result, in addition to doing object decomposition, we can also do functional decomposition also when it comes to building these kinds of applications. But unfortunately, though, if we look at functional programming as using immutability and building with higher order functions, that is not that exciting to me, because what it tells us is how we do things, but it doesn't quite give us the gist of what we are trying to achieve. So to me, really, functional programming is equal to it's declarative style. So declarative style plus the use of higher order functions. But the question is, why do we care to do this? And to get to the bottom of this, the real gist in a sense is it's functional composition plus the use of lazy evaluation. And to me, these are the most important characteristics of functional programming. So you're using functional composition and you are using lazy evaluation. So what is functional composition? Functional composition is really a way to do pipelining. Martin Fowler talks about it. If you Google for this, you will find it. So if you Google for Martin Fowler and then look for the words collection pipeline pattern. So if you look for collection pipeline pattern, what you're going to look at is a way to conceptualize your problem into the series of pipeline of transformations where the data transforms or flows through a pipeline of transformation. Once you conceptualize this particular pattern, you express your problem as a series of transformations rather than trying to think about this as a state mutation. So in that regard, we can look at the functional composition like so. So we can take, for example, list of integer, let's say, we'll call it numbers, if you will, is equal to, in this case, let's say, arrays.asList, and I'm going to take a bunch of values, let's say, these particular values. So, but once I start with these values, what I want to really do is to perform a transformation. So what I can do is we can say numbers dot, and then we can say stream, where a stream is an internal iterator, and we can say filter, given an element mod 2 is equal to 0, so we get all the even numbers from the collection. We perform a map operation, given an element, get me the double of the element. In this case, we could even say map to integer, and then we could eventually say, in this case, perform a sum operation to get the total of double of all the even numbers. So if you look at the code over here, this becomes essentially a functional composition, and it gives us a result of 24. But in this case, the collection of numbers has been transformed to a collection of filters of even numbers and a collection of double of even numbers, and then we totaled it. Now, when you look at a code like this, it begs the question, what are we really dealing with in this case? So I want you to spend a minute on list, if you will, versus if you think about stream. And this realization helps me quite a bit to rethink about what this pipeline means. So what is a list? I want you to think of the word bucket for a minute. So what is a bucket? A bucket is what you use to store liquid. Maybe you have a very delicate cloth to wash, and you don't want to put into a machine to wash it. So you have a bucket of water, and you sink the cloths in the bucket of water, let it soak for maybe several minutes, and then you take it out and wash it. Or you could have a bucket of water where you save water for maybe gardening this afternoon. You want to take it to the garden. So a list is like a bucket. You store things into it. On the other hand, a stream is not a bucket, it is a pipeline. So you don't use pipeline to store liquid, you use pipeline to flow liquid through it. So there's a very different conceptualization and abstraction. A list is a data structure. A stream is an abstraction you are dealing with. So a bucket of data, if you will, but this is a pipeline of functions. And that is one clear distinction between a list and a stream. A stream is a collection of functions, a pipeline of functions rather. So what is the pipeline of function right here? If you take the stream that you have here, this pipeline contains the function which is going to apply filter on it, and it contains a function which is going going to be applying the transformation or doubling of the values. So a stream is a collection of a pipeline of functions where a list or a set is a bucket of data or a collection of data. So in other words, we are conceptualizing this as a series of transformations where we apply the data, but through a collection of functions. And as a result, we're conceptualizing the problem as a series of transformations where we have these functions. But a more important characteristics in here is this idea of laziness or lazy evaluation. So to understand this, let's take a slightly different example of this to understand the capability in here. So imagine you have a 1, 2, 3, let's say 5, 4, and then I'm going to say over here 6 and 7 and 8, and who knows, this could be going for a long range of data, maybe even a million piece of data over here, who knows. But imagine that's what you have. And what you want to do in here is, let's say, find the double of the first number that is greater than 3 and is even. So if you want to find the double of the first number that's greater than 3 and is even, how would you write this code in imperative style of programming? Well, the first thing you would do is result is equal to 0. That's what you would start with. Then what would you do? You want to output the result when you finally get it. Then you would say for, in this case, element E coming from the numbers collection. And then you would say if element is greater than 3 and E mod 2 is equal to 0, then you want to say result is equal to element times 2, but you better do a break. If you don't put a break, you may get a wrong result or a poor performance or both. So you want to make sure that it works properly. Now, this is an imperative style code. When we run the code, of course, it gives a result of 8. But what is the problem with this code? Well, we may not see the problem in the beginning, but this often happens when we write code. I've got some wonderful testers. My tester would walk in at this point and tell me, hey, Venkat, your code sucks. And I always tell my testers, don't tell me the obvious. Don't tell me my code sucks. Tell me how it sucks today, because every day my code sucks differently. And my testers would tell me they tested my code, but with an empty collection. And guess what? It gave a result of 0, which is wrong. Because if a collection has no data, how could 0 be the valid result? Or they tried it with a collection with no value greater than 3, or a collection with no even numbers, and it's broken for all of those. How do you fix this code now? To fix the code, obviously, you will change this to integer, and then what would you do here? And you would assign this to null. And we know what null is. Null is a smell. And immediately your code begins to smell really bad and bugs creep in. Then you have to come in here, unfortunately, and you have to write another piece of code right in here. And what do you do now? You would have to come down to the bottom of this code and say, if result is not equal to null, then you print that result. Otherwise, you may print out something along the lines of, no value. And of course, you could run the code this way to write the code. It still gives you a 8 as a result. But if the value doesn't exist, it would have said no value. But you can see the code becoming smelly as time goes on. But instead of writing code like this, what you could have done is you could have used the functional style. You could have said output, for example, and then you could have said numbers.stream right now. And once you get the stream, you could, not that one. So what you could do here is you could say stream, and then you could say dot filter, and you can say given an element is greater than 3, and you can say dot filter one more time, given an element mod 2 is equal to 0. But then you could have said a map, and given an element, you could have said element, times 2. But then you can do a dot find first over here. And when you do a find first, you are going to get the value. Then you can say, or else, if the value doesn't exist, what do I want to do? Well, if I don't have the value, I could simply return a no value, and I can return that particular response from here. But obviously, it's complaining a little bit that it's not able to return a string, but you can maybe change that to a given element. You could return the element.toString to return a string of that value, and you could execute that particular code to get a result of 8 in the end. But if you look at this code, this becomes a series of transformations, as you can see. But obviously the question is, if the code is beautiful like this, what about the performance? What if this code, this particular thing had 10,000 elements or 1,000,000 elements? Are we going to waste time computing this? Well, this is one of the beautiful things about the functional style of programming where implemented correctly is notice the stream is a stream, filter returns a stream, and the next filter returns a stream, the map returns a stream, but the find first returns optional. Now, how does this code really work? And that is one of the beauties of the functional style. Streams have a very special semantics. And so what do streams do? Streams have a characteristics I've only seen among my children. Both streams and my children are fundamentally lazy. Now, I'll share with you a story of what I've noticed in my house. My wonderful wife, and I've got a bunch of boys at home, you know how lazy they are. And my wife, wonderful wife, will tell my son, turn off the TV. It's like no voice was spoken because the TV is still on and he's still watching it. And then she tells him after that, she says, go put the trash out. And no muscles were moved. He's still sitting and watching TV. Then she tells him, do your homework. No pencils were picked and it is still there and nothing happened. And then she says, I am calling daddy. And immediately everything works. So this they could have called it, and it depends on the, they should rename this method as call one of the parent. And it depends on the family. I always say the parents play the role of a good cop and a bad cop. You know where I'm going with this. My wife is the good cop, I'm the bad cop. So the minute she says I'm calling daddy, everything gets done right away. And this is exactly how streams work as well. You go to the stream and say filter, it says maybe another time. And then you say filter, it says maybe later. You say map, it says maybe after a while. And then you say find first, and it says, oh dear, let's get it done right now. And immediately it acts on it. So in other words, a stream contains two kinds of methods, intermediate operations and terminal operations. And here's the easy way to find it. Look at the return type of all these functions. Every single one of these lines, the return type is a stream. Those are intermediate. But look at the return type of the find first. It's not a stream. That's a clue. It's a terminal operation. So visually, you can immediately know what is intermediate. And so as a result, it's lazy versus what is a terminal operation. As a result, it triggers computation. So going back to this code, if you will, for a minute, let's remove all this for just a second. And going back to this code, let's remove all of these as well, just for a minute. And in this case, I'm going to take this filter and I'm going to simply say sample check, where the check method I'm going to write, we'll simply call this as static Boolean. Well, actually, we'll call this as is even for a minute. And I'm going to say is even takes a number, and all it's going to do is return over here, the return, let's say number is mod2 is equal to 0. So when I execute this code, after all, well, it doesn't have a response right now. Don't worry about it. But I'm going to put this word done over here and fire up this code, and it says done in the very end. But if I go back to the is even function and I output called for, and I'm going to print the value of n, so you can see that when I execute this code right now, it says call for 5, call for 4, and it said done at the very end of this. However, if I go back to this code and if I were to put a semicolon right there and comment out that code, what's going to happen? Well, now notice the terminal operation is not there, but these are all intermediate operations. How does this code work? I'll tell you how this code works. Imagine on January the 2nd, the boss calls you into the office. And the boss tells you, you're going to work on a very important project and it is due on April the 15th, and tells you about the project. What do you do on January 2nd when you get out of the boss's office? You go to your desk and you immediately start working on it, right? Yeah, I like that laughter, right? Because you know the rest of the story. You will start it promptly on April the 14th, isn't it? Because it's due the next morning. What is that called? Efficiency, isn't it? And this is what really efficient people do. Most efficient people in this world are fundamentally lazy. And of course, you know something the boss doesn't know. You know you have already decided to quit on March 1st. Why in the world would you waste your time doing something you're not going to be part of eventually? That's exactly what this code does. When I execute this code, notice it says done, but it never evaluated the is even. And the reason for that, of course, is that it's a lazy evaluation. So the laziness is extremely important when it comes to functional style of programming. So efficiency and lazy evaluation go hand in hand. And I'm going to say efficiency is attained not by doing things faster, but by avoiding things that shouldn't be done in the first place. So if you want to really make something faster, don't try to speed up your computation, but instead try to remove stuff that shouldn't be done in the first place. Now, this is another way to think about it. I live by the mountains. And one of the things I'm always afraid about is what happens when you're hiking and you run into a bear. Now, this happens, unfortunately, hopefully not too frequently, but it does happen. Somebody is hiking and a bear, comes along the way. So, and over the time, I've learned a trick that is very comforting because somebody wise once told me, when you see a bear, you don't have to run really fast. You just have to run faster than the person behind you. And this, I think, is a really great advice. And this is exactly what I look for in case of efficiency, is that you don't want to do work really fast. You just have to do fast enough. And that is something you can do to make this more efficient. Well, that brings us to reactive programming. What in the world is reactive programming? Why do we really care about it? And the answer to that question is, reactive programming is not new, but the name was given relatively new compared to it has been around for a very long time. There's been applications that have been reactive for quite a number of decades now. I'll mention a few as we go along. But why care about reactive programming today? Well, one of the reasons is the world we live in is quite different today compared to only 10 to 15 years ago. I'm almost nostalgic when I say it. I remember waking up in the morning and turning on my coffee pot, and I can hear and then start dialing my modem, and I can hear my modem connect and reconnect, and the whoosh noise of a modem, I can still hear it. And of course, then I'll call my friends and ask them what baud rate they're getting that morning. Well, those days are gone, long gone. Every one of us is connected to our internet all the time. I've got services on my mobile devices. I'm connected all the time. And every one of us carry multiple devices. I'm not talking about smart watches. I'm talking about earrings and nose rings and tongue rings, all internet enabled. And very soon we can have doctors monitor our health, and they could call you right now and say, hey, we notice your blood pressure is really high. Your heart rate is weird. Just sit down and be careful. You can tell them, no, I'm listening to this weird guy who's speaking too fast. That's why my blood pressure is increasing. But the point is that we are not far from the days when we could be continuously monitored. In that case, of course, what we're dealing with is big data, which is high volume data and also high frequency data. Now, of course, with all these internet-enabled devices, we are also living a very different world today. 10 to 15 years ago, companies developed products for their employees to use and made those employees available to the customers. When employees use your product, there's a name for them. They're called captive users, meaning nobody cares what they think about. On the other hand, today we build applications for real-world users to use. If a user is not if the application is not responding well enough, you're going to lose the users. So from that point of view, reactive programming has a few essential things, and mainly it is about responding to the stimuli. Now, why do we need a different model? We talked about it. There are different problems we live today, the world full of electronic devices, big data, and a demand on the application's performance, and of course, different user base as well compared to where we are. But if you think about it, These applications have been around for a very long time. I'll give you two examples of reactive applications. One is very old. One of the best examples of a reactive application, hands down, is Microsoft Excel. Think about Microsoft Excel for a minute. Everybody uses that. Offices use it, homes use it, and anywhere in between we use it. But you modify a cell, and before you could blink your eyes, all the cells that depend on it change right away. And in turn, recursively, all the cells that depend on those cells change immediately. That's a beautiful example of a very highly reactive application. But I'll give you another example, and this almost slipped by me without me thinking about it. I travel almost 100%. I'm in a random part of the world almost every week. And which really brings the question, how do I communicate with my family if I'm traveling so much? Well, we're an electronic family. We constantly communicate with each other through electronic documents and that we exchange. But I didn't realize this until one morning. I was in a remote part of the world and I logged on to Google Docs and I found that my wife was editing the document exactly at the same time and back at home. And it occurred to me immediately, I scrolled down to the document and I can actually see the exact location where she was typing at that moment. So immediately from tens of thousands of miles away, I put my cursor exactly where her cursor was, and I started changing the text that she was changing. And with this, I found out the real benefit of reactive programming, because you could be thousands of miles away and still find a way to annoy your spouse. And this is amazing, because for her to tell me, get out of my document now, was absolutely priceless. And then I sat back and thought about it and said, how wonderful this is, not the annoying part, but how wonderful this is that I could be anywhere in the world and collaborate with people who are anywhere in the world. I'm on Google Docs where I am talking to my customers, or I'm talking to my conference organizers, or I'm talking to my program committee, and I'm constantly talking to them. And we have 10 people, 20 people, 30 people jump on a document, and we are able to interactively update at exactly the same time. But on the other side, think about Google Docs itself. Literally, they have millions of people editing documents and getting response right away. That's a great example of a reactive application in terms of the stimuli and how we can respond. So the question is, what does it really mean to create reactive applications? If you look at the past, you can ask people what kind of applications they were building. And a lot of us still build applications like it. And we can summarize that into one acronym called CRUD. We create data, we read data, we update data, and occasionally we delete data. So what does this really mean? You have a data in the database and you pass it to a process, and then what do? You take the processed data and you put it back into a database. Now, if you really think about it, try explaining this to somebody. They ask you, what do you do for a living? And you say, I take data from a database and I put it back where I took it from. That's a very boring life, isn't it? And they look at you and say, where do you go to work for doing that? And that's kind of what we've been doing for a long time. We've been just taking this data and putting it back into the database. And then suddenly you look at this and say, maybe everything doesn't fit into it. What if I'm interested in monitoring tweets? What if I'm interested in noticing what people are saying about a particular product? Or maybe I want to know what people are saying about a particular team while the game is on, or whatever that could be. You don't read this from a database. There's a data flowing through and you're processing it. What if a credit card company calls you and says, we want you to help us to do fraud detection? And you say, yay, I'm going to do ML, machine learning, and I'm going to implement a process that will tell you if there is a possibility of fraud in the transactions that flow through. But what database is the data going to come through? Well, a credit card company is going to process millions of credit card transactions every instant. There is no tomorrow in this case. You don't store all this data into a database only to come back and process it. As the data is flowing through, you want to detect any fraud in that and immediately respond to it. And this happens to me quite effectively. I traveled so much. I would perform a transaction, and within minutes, my wife would get a call at home saying, "We don't understand this. Your a credit card has been compromised. We see a transaction yesterday in Barcelona. We see one the night in Riga. The third day we see one in Lisbon, and a fourth day we see in Amsterdam or Australia for that matter." And then she usually says, "Yes, that's called being married to a crazy person. And so don't call again if you see this." But this is a way to detect fraudulence, probably to say, this pattern of movement is not normal. What's going on over here? Maybe we should trigger this. So how do you really process that? In that regard, we are moving towards taking the data from a database, data as it flows through rather, and send it to a function, and then take that and send the process through. And so we go through a series of transformations. A data that arrives at your door is processed, and you get a new data, which then is processed to get a new data, and that flows through. If you have been around in the 1980s, you could not have survived 1980s without hearing this word called data flow computing. So data flow computing was big deal back in the 80s. And even people started building data flow computers. One of them was called Manchester Machine. And then, of course, in the late 90s to early 2000, it quieted out. Nobody talked about it. And I used to wonder, why don't anybody talk about data flow computing? And then suddenly, in the past few years, I started hearing people talk about it again. Now, what if I tell you, I got a great news for you? You can do data flow computing. You're probably going to look at me and say, "Grandpa, sit down. That's not exciting." But I'm going to sell it to you in a way you will tell me this is the most amazing thing ever. What if I tell you, you can use Amazon Lambdas and you can do serverless programming? You're like, "Oh my gosh, this is awesome." In so many words, I told you, you can do data flow computing. And that is the fun of the field we live in. You suddenly hear people talk about serverless computing and Amazon Lambdas, and you're scratching your head. Why are you renaming data flow computing all the way again? Because the new kids are like, this is exciting. So serverless computing is rebranding of what we did in the 80s. It's really data flow computing. So in that regard, I'm going to say reactive programming is data flow computing, and that's what it really is. It's a series of transformations where we take the data and transform it using a series of functions. So if you ask me, what is reactive programming? I'm going to say reactive programming is applying a series of data transformation. It is a streaming of data as we transform through it. That's what we really are trying to do in reactive programming. So in that regard, what does reactive programming really insist on having? It's a streaming of data. So think about data flow computing, and it's a series of transformation of the data that you're going to provide. But obviously the question is, if that's what you're doing, what does it really mean to create applications with this? So in other words, there are a few criteria we're going to apply for this particular purpose. Now, before we talk about it, let's talk about object-oriented programming for a minute. OOP has 4 pillars of the paradigm. The first is, of course, abstraction. The second, of course, is encapsulation. And then, of course, we also have inheritance, which is the weakest link, if you will, the most useless of all the 4. And then finally, we have polymorphism, which is probably the most important next to encapsulation. So given this, of course, we have these 4 things that contribute to OOP. Similarly, reactive programming also has 4 things as its paradigm. So what are the 4 things that it really represents? The very first thing is, when you build reactive programs, you're really aiming for big data, a very high volume, high frequency of data. So that means you are really focused on scale. I was talking to a customer of mine and I asked them how many people typically use your application. And they said, oh, on a given day, I asked and say, on a given day, about 100 people use. And I was surprised. I said, 100 people? You're a multi-billion-dollar company. Only 100 people use your product. And they said, yeah, you asked on a given day, but over a 48-hour period every month, over 70 million people use their products. How do you go from nobody cares what we do for most of the month and 70 million people use our system in 48 hours? Well, you cannot possibly do this by keeping a staff locally in your building to manage all these servers. And we have learned the lesson really good over the past decade is being elastic. So elastic computing simply, as the word elastic says, we grow when the demand grows, we shrink when the demand goes down. So we can bring in processors when the demand goes up, either based on the demand or the time of anticipation, and we can bring it down so you only pay for what you use, not other things. And that can be really powerful way of using the systems and to scale based on that. So elasticity is one important part of it. The second thing, of course, is how do you exchange data between all these different services? And the answer to that question is we got to have the data that flows through, but how do I make the data flow through? Let's talk about a way we should not approach this. This is true for reactive programming. This is also true for microservices. I was in a meeting at a client site. We were talking about microservices. Everything was going well. And remember, one of the characteristics of microservices are that they are autonomous. You want to be able to build microservices, start them, and manage them in isolation and independent of other services. So this conversation with the client was going really well until suddenly one of the people in the room asked the question, how do these microservices talk to the central database? And immediately the entire room went quiet, like somebody died in the room, because that's such a disastrous way of thinking. Because if you have a central database, you modify the schema on the database and all the microservices come crashing down. They're not going to be able to be isolated and independent. So I have a slogan. I have a philosophy of life. And I hope you agree with this philosophy. And the philosophy of life is both in life and programming, we should never share two things. And this is something I teach my children from the very beginning. Both in life and programming, we should never share two things. The first is a toothbrush. And the second one is databases. And we should never share. And very rarely, I may even share a toothbrush, but never a database. And the point really is that the minute we share these things become really unhygienic and becomes really problematic over time. So this is something to think about. So how do you really exchange data between these services? And the answer to that question is really you want to focus on message-driven, and you want to be able to drive these through message-driven. And as a result, you could use things like Kafka Stream or other ways to communicate your messages. And these services and all these processes or functions are going to do message exchange through message-driven architecture. The next thing about reactive programming is really to be able to be responsive. So what is responsiveness? The application we quit using today are the applications that are going to take a very long time to respond. We live in the age of instant gratification. We want things to work really, really fast, and we're not going to wait forever for things to spin. Now, a really good example of responsiveness is infinite scrolling. Remember the first day you came across infinite scrolling. This application was slow and sluggish, but that morning you went to the application and snap, you got an output. And you're like, wow, that's interesting. That worked really fast. I wonder why. And you scroll and your brain is telling you there's no bottom when you scrolled. And before you could think about it, the bottom gets filled with more data. And as you scroll, the data comes in. That's a really good example of being responsive. The goal is not to work really hard and produce slow results, but to the minimum to get something to the user so they can be productive with it. And then you amortize the cost of doing it over time. Here's a way to think about it. You walk into a store on a Saturday morning, the clerk is busy at the store helping somebody. What are you going to do? You're going to walk around for a few minutes, look at the ceiling, look at the wall, look at the floor, and you walk away. On the other hand, you walk into the store, and the minute you walk in, the clerk makes eye contact with you and says, I'll be with you shortly, and goes back to help the customer that was there. You probably waited for a good 15 minutes at that point. Why? Because you felt important even though you are not. And that is one of the ways to really think about it is you built loyalty by being responsive, and that is something you can really do. Well, the fourth part of this component really is that you want the applications not only to be responsive, you want them to be resilient as well. So resilience is a very important characteristic. The applications we quit using are the applications that are going to fail in a very ungraceful manner. So what if we treat failure as a first-class citizen? What if we say it's okay to fail and we will promote failure in a graceful way and we can recover from it? Now, I want you to ask the question, can there be an organization today that creates a terrible application and users will still use it? And the sad answer to that question is yes. And that is called the Russian government. And I'll tell you why. I have this wonderful, I'm thankful for this luxury. I can travel most of this world without having to get a visa. I just fly in and they say, thanks for coming, and they let me in. But of course, I got to apply for a visa to go to Russia, which is great. But I applied for the visa. And the first page was pretty easy. I entered my name, address, phone number, great. The second page, not too bad. The third page is the worst of the page. It said, list all the countries you have traveled the past 10 years. Are you kidding me? And it took me forever to enter all the 200 countries I've been to in the past 10 years. But this is called the curse of a programmer. When you're a programmer, you think of every other programmer suspiciously. So as I was entering the data, I am like, how well is this going to end? So everything I type in the form, I'm literally copying and pasting into Notepad and saving it. I come to the fifth page, click the button, and it's gone. I'm like, are you kidding me? After spending an hour and a half to 2 hours entering all this data, it's gone. What do? Start over. And now I'm copying and pasting a Notepad into this application and coming all the way to the end. And there was the submit button. Clicking on it is called hope. And I did. And it failed the second time. In the US, we have a saying, the third time is a charm. I wanted to give it a try. And yes, it did work the third time. But I still used it. Why? Because I'm the captive user to the government at this point. And people who have applied for visa to the US government have said that is true for the US government too. I'm so happy we actually suck the same. But the point really is that any business in the private industry will not survive this. You would go to another product and use it. So unless you're a captive user, you're not going to listen to this. This reminds me of an experience I had. I was speaking in a conference, and at the end of my talk, a gentleman in the conference came to me and said, hey, Venkat, you probably don't remember this, but I was your student, he said, back in 1998. I took your distributed object computing course. I've been teaching at the university for a good 30 years now. And I told him, oh my goodness, I remember back in the 90s teaching distributed object computing. Remember I mentioned about Common Core. So, and he said, well, I have a story to tell you. I said, oh, I love stories. Tell me the story you have. And he said, well, I was in your course, distributed object computing course, and the course had a final project. And I was demoing the final project. And in the middle of my demo, you got up from your seat. You walked over quietly to my machine, disconnected my internet cable, went back and sat in your chair, and you said, continue. And my program crashed because there was no internet connection. And I failed the course miserably. I said, oh my gosh, this is not a story. This is a tragedy. Why are you telling me this after all these years? And he said, well, I'm telling you this because there is a happy ending to this. I said, how could there be a happy ending if it starts with the failure of my course? He said, you see, you taught me a very important lesson that day with this experience. You taught me not to focus on the happy path, but I should program for resilience. He went on to say, today I work in the industry, but I'm a lot better than what I was before, thanks to you, he said, because in my office, in my cubicle, on the wall, I have a picture of evil Venkat. And I look at this picture every day and I never make the mistake again. Honestly, I don't know how this picture looks like. But the point is, I don't think we need a picture like this. We have to program for resilience. That's absolutely important. So the question is, how can we build resilience into the application? And the answer to that question is, we want to deal with exceptions as a first-class citizen. The worst thing we did in our industry is call exceptions as exceptions. We should have called them normal, because stuff happens and you have to deal with it. So if it was normal, we will deal with it properly. Exceptions, unfortunately, are an imperative programming idea and doesn't fit really well into functional programming. With that said, we talked about all these parts over here about reactive applications, but moving a little further, how does this really relate to? Well, this is where let's talk about writing a functional interface to do what we really want to do. So to get a feel for this, let's take this example and write this here as really a functional API. That is being reactive for reasons I don't know. But let's take a look at this right here. So what I'm going to do here is that we're going to use a generation of a number just to give you an idea about how this works. So let's go ahead and start with a flowable in this case, and a flowable of, let's say, integer. I'm going to call it as create, and I'm going to take an emitter, and I'm going to pass it to an emit function at this point, and I'm going to, don't worry about the back pressure. Right now, we'll talk about this a little later. Then I'm going to create this emit function. So what am I going to do in the emit function? In the emit function, I'm going to simply say over here, starting. That's all I'm going to do. Now that I've said starting over there, I'm going to come back to this code and say, let's move forward. But when I run the code, notice it did not call the starting. Why? Well, that's because it's lazy. It's not going to do the work until you really use the result. You can tempt it. You can go to it and say a dot filter, and given a piece of data, data mod 2 is equal to 0. And the reactive library says, I know what you're trying to do, but I'm still lazy. So you could even tempt it even further and say a dot map, and you can say given data, data times 2. And of course, it doesn't budge yet, as you can see. But then you say dot subscribe. This is like the call daddy or call mommy function. And then you say system.out println, and now it says we got a deal. And you can see that it says starting because you have connected to it with the terminal operation. So you can see the functional composition and you can see the lazy evaluation right in front of you. So this is one of the reasons why I say that reactive programming is functional programming plus, because we start with the function composition and the lazy evaluation, and then we build on it. So what does that really mean in that case? So I'm going to say reactive programming is equal to functional, let's say functional programming, because we are talking about composition plus lazy, and then plus we are going to say that in this case, we're going to add something more to it. And we'll see what we are going to add in just a few minutes. So we are creating this and we're going through this lazy evaluation. Now what we can do in here is we can then say, well, int count is equal to 0, let's say. And at this point, what I want to do is say while count is less than, let's say plus count is less than 10. But I want to now say over here something along the lines of emitter.onNext. And I'm going to send the count over here. And then, of course, I'm going to do a sleep of, let's say, about half a second. So I'm going to sleep for half a second right in here. And once I sleep for half a second, what am I going to do at this point? Well, actually, let's go ahead and write a sleep function right here and then be done with it. All right. So that's going to be sleeping for half a second and move on. This is going to emit the data. Well, that's great. It's going to emit the data. From that point of view, if it is going to be much like a stream as a functional composition, then what is the difference between those two? And I want to quickly draw some similarities and distinctions just to understand this. So Java stream versus what I want to call as a reactive stream. Well, both are really pipeline and functional composition, right? So both of them do a functional composition and pipelining. So that is common to both of those. Both of those have lazy evaluation, and this one has lazy evaluation also. but the similarity ends, unfortunately, right there. So what happens further down? In the case of a stream, you have a data channel, a channel only. So all you transmit in a Java 8 stream is data. And in the case of reactive stream, a data channel also. We'll understand what that means in just a minute. But the most important question to ask is, what about errors and exceptions? Well, I can answer that question in 2 English words for Java 8 stream, and that is called good luck. Because if your code blows up, it causes havoc. There is no real good way to deal with it. Why? Because exceptions are really imperative programming ideas. So exceptions are imperative programming ideas. Now, what do you do when an exception happens? You blow up the stack and you go back to the call where the try block is. What does that mean in functional programming? You remember the functional pipeline. Imagine a friend of yours, he is driving on the freeway and poof, they get a flat tire. And they call you and say, hey dude, I've got a flat tire. What do I do? What's the worst thing you can tell them? You tell them you got a flat tire, now drive in reverse. It makes no sense, isn't it? But as a good friend, unless you're trying to kill them, what you would tell is safely exit the freeway and get out. So the idea really is, how do you deal with this? And the way you deal with in reactive stream is deal with it downstream. So you want to deal with the downstream. I'll give you a quick example of this. I was in Boston to speak at the Java user group, had a great time. The next morning I had to go to Montreal, and I said to myself, I'm an international traveler. It's just across the border. It is not a problem. It's a different country. I can take this. Well, my flight was at 6:30 in the morning. I decided to go to the airport at 4 from the hotel. Well, it had really snowed the last night. The road was covered with snow. I started driving at 4 in the morning. There's nobody around me. And within minutes, I hear this boom. And the next thing you know, the car is not moving well. I stop the car, take a look at the tire. It's completely busted. And I'm thinking, what do I do? And since there's nobody around, I picked the phone and called the towing service. And they said, you're a valuable customer to us. Thanks for calling. We'll be with you in 2.5 hours. That's not going to help. And I sat there thinking, what do I do? Honestly, reactive programming came to my mind. And with good courage, I turned on the ignition, put my foot on the gas pedal, and I drove the car all the way to the airport. And as I pulled into the parking lot of the rental car company, you'd have seen the people over there. They were like, what in the world is this huge noise? And the guy came over and said, are you okay? What's going on? I said, oh, just a flat tire. Here's the key, by the way. And I walked over. And this is when you're so happy it's a rental car. Well, a few weeks went by. My wife called me and said, remember that story you told me? I said, yes. Well, you got the bill in the mail. I was like, oh, let me sit down. What is it? She said, oh, they charge you $85. I can handle that. Well, the point really is you deal with it downstream. How do you do this? Well, the way you do this is in the reactive stream, the flowable or the observable have 3 channels that they provide. The first is the data channel. Through the data channel, you get the data. So what you saw up here is that you're subscribing to the data channel. So when I run this code, you can see that it is giving us the 4, 8, and 12, and so on. That is data coming through the data channel. Well, that's great. But what's going to happen if things were to go wrong? You have an error channel, and through the error channel, you get the error, and there's a complete channel through which you'll get a complete message to signal that there's no more data coming in. But the way this works is, if there is an error, you get an error through the error channel, but the data channel will close up. So you're not going to get any message through the error channel. But what happens in this case is that it treats. So what do you do in here? Instead, what you do is treat error as data. So you're treating error as data. So you're not treating it any differently. If something were to go wrong, I politely give you an error rather than throwing things at you. How uncivilized that would be. So how does this work? Let's understand this in this example. So I'm going to go back to this code. As you can see, it produces the data 4, 8, and so on. But I'm going to subscribe to the error channel. So error, and I put an arrow, and I output error over here. So let's say error. And then I'm going to then simply display right here the error message. And then I put the complete channel. And in this case, I'm going to simply say done to display it. Now, when I run the code, obviously, it just goes through it. But what if something were to go wrong? So notice what I'll do here. I'll come into this code and say if, and I'm going to say count is equal to, let's say, 7. Then what am I going to do? Throw new runtime exception. So I'm going to blow up right in the middle. Let's send a message like we often see in our production. Something went wrong. So this is going to blow up right in the middle with such a useful message, isn't it? And as a result, what's going to happen when you run this code? So when I fire this up, you notice it starts processing this one at a time. But when the value hits a 7, it immediately says something went wrong. But notice the word error over here. So your exception was captured, the data stream was closed, and the error message is delivered to you by hand at this point through the error channel. Similarly, of course, if you don't have an error, then what's going to happen really is it is going to go all the way through, and then you can say emitter dot on complete, and you can send a complete signal. And notice at the very end of this, you will see the message done being printed, and that is coming from the complete channel, as you can see right in there. But there's one small problem with this code still. And that problem really in this case is what's going to happen if when I receive this, I'm going to take this one and say a sample, let's say in this case sample, and I call a process function. So what in the world is the process function? Well, I'm going to write the process function, receives the data, we'll call this data, but I'm going to unfortunately here output the data, but I'm going to say sleep of 1 second. Now notice there's a half a second delay in sending the message here, but a 1 second delay in receiving it, which is really unfortunate because it doesn't go really that fast. As you can see, it's much slower. So what you can do to get around this problem is to make it asynchronous. So what you do here is you can say, in this case, observe on, and I'm going to say this is going to be schedulers dot, let's call it IO, not going into the detail right now. And I'm going to specify that is going to be on the schedulers, and I fire this up this time. But notice in this case, it is, well, actually to see this a little bit better, let's do one more thing. I go to the emit function and I'm going to simply say output, we'll say emitting over here and then display the count over here. So when I run this code, you can see it's emitting much faster than I'm processing it. But how is this working? Because I applied this idea of back pressure. So what is a back pressure? A back pressure is where you let the producer run in a very different pace as a consumer or a subscriber, and one doesn't control the other. And of course, in this case, you can use different strategies. You can say drop if it makes sense. And when you run the code this time, notice that 1 and 2, but you process, you know what, to keep this a little easier to see if you don't mind, let me just do data times 1 that way, and I'll remove the filter so we can see the processing in a lot better way. So notice 1 and 2, but 3 and 4 was not processed. We have 5 and 6 was processed, but 7 and 8 were skipped, and you see 9. And the reason for that is we did a drop strategy compared to if we say buffer, you can see that it's going to buffer it up, and all the values 1, 2, and 3, and 4, all of them are processed and until the very end. Of course, in this case, I want to keep it a little alive. So let's go ahead and do that for a second to see that working. And you will see the buffering come through, and it's not going to lose any data at this point, and it's buffering through them and displaying the results right after. So to summarize what we talked about here, reactive programming is functional programming plus the use of back pressure. So as a result, and plus the use of 3 channels of communication. So you are building up on this. So essentially what you're doing is you're taking this idea, the central idea of functional programming, and you're building abstractions on top of it. And you're bringing in the back pressure into it and the 3 channels of communication into it. And on top of that, you could be adding some flavors to this. For example, you can say either synchronous, potentially, or you could be using asynchronous as well. So you can decide which way to go based on your problem needs. So you could be doing synchronous evaluations or potentially an asynchronous evaluation. So the reactive programming ideas start with the ideas of functional programming, and then you build on it with back pressure, the three channels of communication, and the synchronous versus asynchronous communication as well. And that's basically what we saw here is as a bridge between these in terms of how we evolve. So to summarize what we talked about, the ideas of reactive programming are very fundamental to creating a highly scalable and efficient and performing systems. But these ideas are not just isolated. They nicely built on the ideas we're already familiar with by introducing a few concepts and merging them together. And that's basically my journey in learning this, in trying to figure out what this means. And putting it in that context helped me really understand how I